All right, let's continue with our probability slides. The next thing I want to talk about is a good use case of conditional probability. It's a very powerful thing. It's called Bayes' theorem, or Bayes' rule, you might hear it as, but it's really nice. It lets you flip your conditional probability. So sometimes like the probability of B given A, that's like an easy thing to calculate, and then it's also easy to calculate like probability of just A and probability of just B. But really what you want is the probability of A given B. You want to flip this. All right. If you have all these three things, you can flip it. It's really cool. All right, here's the formula for it. Probability of A given B is equal to, well, you know what it's really equal to. Like, you can do it the real way with this formula, or it is also equal to this in terms of the other one. It's probability of B given A times probability of A over the probability of B. Isn't that cool? And here's why. Let's prove it. So, proof of the formula. It's going to be, we know the probability of B given A, right? We have that. Let's assume that we have that number already. But if we have that number, what does that mean for us? Probability of B given A. What is that in terms of the original definition of conditional probability? It's the probability of their intersection, right, over the probability of A. Probability of A intersect B or B intersect A. It's commutative, right, over the probability of B. Sorry, just A. Got it backwards. All right. So do you see how? Let's do some math. If you multiply this probability of A on this side, you'll get just the probability of their intersection. So that's, you can turn that into this, probability of A times the probability of B given A, which you assume you know. That will give you the probability of their intersection, probability of A intersect B. See how that's useful knowledge? Because you can go from this to, like, what do you really need, like, for the probability of A given B? Probability of A given B, that's equal to the probability of their intersection over the probability of B. Do you see how you have a way to get this by taking all this? Take this guy. Let me use rainbow or something. Take this guy. Boop. Place it right there. Because that's another way to get the probability of A intersect B. You see that? You have this, you have this, you have this, you have those two numbers, multiply them together, you have another way to get their intersection. So that's how you get this. Does that make sense? That's how you can get that. And then you have probability of B already, so just like divide by that. So you're good. So that's a very useful thing. Very useful thing that you can use. That's going to help us in a lot of problems. You can even get away with knowing a little bit less than this if you know something slightly different. So if you don't know the probability of B, because you need to divide by that, but you do know the following. If you know the probability of B given that A did not occur, given A bar, the complement of A, there's a way to calculate the probability of B with those things and just the probability of A. So like it's equal to that plus that. So you assume you have these already, that guy, assume you have this guy. It's very easy to calculate probability of A bar. It's just 1 minus probability of A, and the probability of this. If you have that instead, you can get at the probability of B, what you needed. All right? So let me kind of prove that to you in a hand-wavy way. Because if you think about it, like here's A, some events, right? Here's A, here's B. Maybe they've got some intersection. Boop. Boop. So they look like that. If you think about it, the probability of B, what is that? It's equal to, here's kind of what this is showing you. The probability of B is equal to the probability of A intersect B plus the probability of A bar intersect B. Does that kind of make sense? It's like, what does that mean? The probability of just B by itself is equal to the probability of their intersection, so that's that bit. That's this bit. Boop. So you have that by calculating their intersection plus the probability of A bar intersect B. So what's A bar? It's everything that wasn't in A. It's like all these diagonal lines. Everything that wasn't in A. Whee! So that does not include their intersection, right? Because that was in A. Like all this stuff contains a bit of B, right? Intersect with B. Do you see how that picks out exactly, here's everything intersected with B, that picks out everything that was not in their intersection but was also part of B? Do you see how both of those together, their union, makes all of B? And so this is how you get at both of those, the way, like, do you see that that gives you A intersect B, probably A intersect B, and this will give you A intersect B bar. That's the secret. That's another way to get the probability of B. So that's another way to have that. Sometimes it's easier to know this for reasons, but that's Bayes' theorem. All right, there's your formula. You can flip your conditional probability. It's very useful, very helpful. All right, so here's a standard example of why that might be useful. It's a classic example. It's kind of like a paradox because it doesn't make a lot of sense, but like we have the math to show why. Let's determine how good a test is for like an illness, like COVID or something. So let's say that some researchers, they get together, they come up with what they think is a good test for some illness that's affecting the population. So suppose that they made it so good that their test was 90% accurate when somebody had the illness. All right. So what is that but a conditional probability? The probability that their test was positive, given that the person had an illness, that's what their 90% is saying. Does that make sense? So that's what it means. When someone has the illness, given that they had it, what's the probability that you got a positive reading? 90%. And then let's say that the illness is not super common. Just like on average, you take random people, only 5% of a random sample of the population is going to have the illness. So the probability that like a random given person has that actual illness is 5%. All right, which means the probability that somebody does not have the illness is 95%. It's the complement, 95%. 1 minus it. Okay, and now let's keep trucking. Let's say that the test is 80% accurate when someone does not have the illness. So it's a little bit different. It's like a false positive case, kind of, right? So say that it's 80% accurate when someone doesn't have the illness. So that says it gives back negative correctly in that case, all right? So the probability that you got a negative, given that you didn't have the illness, that's what the 80% is saying, all right? So that means the probability that you got a false positive, probably that it was a positive case, given that you did not have the illness, it's the complement of this. Does that make sense? The opposite. It's probably that you got a bad positive reading, even though you really weren't sick. There's a 20% chance of that. All right, so still not horrible odds. So it's usually right? And so now our question is, what is the probability that someone has the illness when you got a positive test back? Because that's really what you want as the maker of this test, right? Given that you got a positive test, what was the probability that the person that you gave that positive result back to really was sick, really had the illness? Do you see how that's really what we want? We don't want this. We want this. We can solve for it now with Bayes' theorem. So what is it? It's going to be equal to, right? Going to be equal to the probability of has illness given positive is equal to this guy. Probability of the flip side, the probability of where am I? The probability of that it was positive given that you have the illness, let's call that HI, times the probability of the original left side, the probability that you had the illness, over the probability that it was positive. But if you don't have that, you can get it by doing this calculation, which we do have right now, all right? So we want this. We can get the probability of that thing by doing these two calculations, which we have both of them, okay? Let me show that to you. It's the probability of this guy, which is exactly the thing that we put on the top half of our thing, on the top half of our calculation. So we just write that all over again, right? It's probability of, so all this all over again. Then we're adding it to something else. Probability of positive given that you have the illness times the probability that you have the illness, and now plus those complements. So we have some useful stuff here. So like we want the probability that it was the first thing given the second thing complemented. So the probability that it was positive given that you didn't have the illness. Does that make sense? So the probability that it was positive given that you had no illness, no illness, NI, times the probability of that complement, probability that you had no illness. So that's another way to come up with the probability that the test was positive. All right, that's what we really want right now in like a population. So that's what we can calculate. And so we just plug these in. We have all these values. Probability that it's positive, and given that you have illness, that's 0.9. 0.9 times probability that you have the illness is 0.5. 0.05. That over all that again, 0.9 times 0.05 plus Now we got probability that's positive given that you don't have the illness. That's 0.2. All right, it's false positive rate, 20%. And then times probability that you don't have the illness, which is a 95% chance you don't have the illness. 0.95, and so that's the math. Let's do the math. I guess we'll come back to this in a second. We got, what do we got? On the top, I'll just do that. 9 times 0.05 over 0.9 times 0.05 plus 0.2 times 0.95. It is apparently about 19%, 19.1-ish%. That's a horrible test. You see that? All these numbers, they kind of look okay, but because that illness is so unlikely, like this false positive rate really blows up, and it makes things bad for us. So the probability that you actually had the illness, given that you got a positive result back, is less than 20%. That's crazy, right? So you really want this to be very low, because that's especially for very unlikely illnesses. Does that make sense? It seems almost paradoxical, but no, just the math checks out. That's how you can solve it, and this ended up being a very bad test because of it. That's why we want to calculate that stuff. That's very cool. All right, new topic. Let's talk about random variables. This is interesting because we know about variables from computer science, and it kind of helps us, honestly. So a random variable is just a name, call it x or something. It's a variable, but it's really a function secretly. It's really a function from, it flips a coin for you almost. It's a function from the sample space of your experiment to numbers. So it's just to any number, to real numbers. You can define it to mean anything. All right, so that's what your random variable is. It's just it's something that if you look at it, it's really a function kind of, but if you look at it, it's every time you look at it, it gives you a different random number back, kind of. It's a variable that if you print it out, it will give you a random number. Think of it that way, all right? And so you can abuse notation, that's the technical term, by giving it the entire sample space, and that will give you back the range of the function. That's what you mean for that. But let's say that we've got a random variable called d, and every time we look at it, it tells us the sum of 2 dice rolls. All right, that's the idea. Here's a good example. It's from your book as well. It's let's make a random variable d to represent rolling 2 dice, and the number that the random variable represents is the sum that we get when we roll the dice. Does that make sense? It's every time you print it out, it's you roll 2 random dice, a blue die and a blue die and a red die, and you're getting back out the the sum of those dice. Every time you print it out, it's a random variable. I hope that makes a little bit of sense. But really, it's involving, it's a number that you give that represents an event that happened, all right? So your random variable d, if you call it, right, it's meant to be a function. D with this event e, it's meant to assign a number for every event. So this event is 5 plus 4, right? So we're going to give it 9. That's what we're trying to represent by this random variable. It's the sum of those 2 dice, all right? I hope that makes sense. And so the random variable would also sometimes give back 5, right? That's a possibility because you could have rolled a 3 and a 2. I hope you see that, right? So there's that. Let's see here. So yeah, d equals 5 is a possible event. It's possible for that random variable when you look at it to give back 5 because you could have been in that event, or some other ones 4, 1 as well, right? So that's all it is. It's it's a variable that represents an event, and it gives a number, it assigns a number to every event. And when you look at it, it's random. You don't know which one you got, but it's one of the things. It's one of the numbers for one of the random events that occurred. All right. So yeah, the range of d, if you think about it, what is the range of your random variable d? It's all the sums that you can get on 2 dice. So you can have 2 1s all the way up to 2 6s, right, and everything in between. I hope you see that. So that's the range of your random variable d. That's the values that it could take on when you inspect it. All right. So there's that. Here's another example from your book. Let's say that we have m as the random variable that represents the sum of a red spinner and a blue spinner. You spin it and it lands on 1, 2, 3 for each of them. All right. So you can think about your outcomes as tuples in this case, right? And then first this one landed on 3, this one landed on 2. It's blue 3, red 2. And then our random variable is going to represent, like it's going to give a number meaning, a single number meaning. It's always to a real number, a number meaning to that outcome. All right, so like 3, 2, the meaning of that is going to be 3 plus 2, or 5. All right, I hope that makes sense. Just you're giving a number to each event. All right, so that's it. It's like it's representing like randomness. It could have gone on any of them. So like anything in that range, for example, for the dice. Okay, next we can talk about the distribution of that random variable. All right, so let's go back to the spinner example. So the distribution of your random variable is like you make a table, like all the ways like that you have this outcome, right? R is one of your possibilities for the random variable's value to take on, comma the probability that outcome occurred. All right, that your random variable took on that value. All right, it's just the probability of each value occurring. You're assigning a number to every outcome. You're calculating the probability that that particular output was reached. All right, so you got a random variable that talks about the sum of two spinners. What are all the different values? What's the range of this random variable? M is just, well, it could be 2, right? It could be 1 plus 1 all the way to 3 plus 3, 2 to 6. And what are the probabilities of each of those? It's like, all right, what are the ways that the random variable gave back a 2? There's only one way, right? The blue and the red spinner had to have landed on 2. Does that make sense? Like those are the ways for M, the random variable, to have given back 2. Do you see it? That's the probability. It's going to end up being 1/9 if you think about it, because we got 3 options for this one, 3 options for that one. So it's one way out of 9 potential ways to do things. All right. What are the ways that it could have, like your random variable gave back 3? There's 2 ways, right? Either the first one's the blues landed on a 1, this one landed on a 2, or vice versa. Blues a 2, red's a 1. You have 2 options over 9 total ways that the spinner could have like done things. So that's your probability, 2/9 for the random variable to have given back 3. Does that make sense? And then same for 4, right? 4 is similar, like 1, 3, 2, 2, or 3, 1. Those are the ways to get it. So you got 3 ways out of 9, so that's 1/3. Those are your chances. And then 5 and 6 are similar. So it seems like it's most usually the case, right? Most often that it lands on 4 rather than something else. All right, that's the most highly probable one. But that's a random variable. It's just like you're assigning numbers to to your events. That's all you're doing. All right, and you can think about like how often does that number end up given the kinds of events that happen in my experiment. Okay, given my sample space. So okay, we can next talk about the expectation. This is an important number as well. So the expectation of a random variable is a number we can calculate. It's a weighted average is all it really is. It's you call it this. You say E, and then in brackets you put your random variable. All right, it's a weird thing to say, but that's it. It's the expectation of the random variable x, and this is how you can define it. It's like the expectation is it's a weighted average. You take all of the events in your sample space, you figure out what the random variable gave back for that thing, and you multiply it by the probability that the random variable landed on that event. All right, that's it. Just like take each outcome, multiply it by the number, take the probability of each outcome in your sample space, multiply it by the value that the random variable gave back, and sum them all up. That's all it is. All right. If you stare at this long enough, there's an easier way to get at it. It's just like for every value that the random variable takes on, this is another way to do it. It's like take that value, multiply it by the probability that the random variable landed on that value. All right, and remember the x of s is the range of your random variable, which is just secretly a function. So it's just a weighted average. It's like the number times the probability that it landed on that number, whichever way you want to look at it. All right, it's just a weighted average, and it kind of tells you what you can expect out of the random variable if you look at it enough, on average, kind of. Okay, so that's how that works. And so let's calculate. Here's how you calculate the expectation of the random variable m. That was talking about the sum of these 2 spinners, right? So we came up with this table. We'll do this one. This is what the calculation we can do. It's the easiest one. Just like, all right, take the number, like sum up all the ways, take the number that, each number that the spinner could land on, like the random variable could give back like 2, and multiply that by the probability that you got that number out of your random variable. So it's 2 times 1/9 for that one. Does that make sense? And you just keep on adding them up. 2 times 1/9 plus, it's a weighted average, plus 3 times 2/9. See it? Plus 4 times 1/3, plus 5 times 2/9, plus 6 times 1/9. And it all averages out nicely to be 4. So the expected value that you can expect to see on average from your random variable, that's giving back the the sum of what the two spinners, right, would give back, you can expect to see 4 on average. Does that make sense? Because sometimes you're going to see big numbers, sometimes you're going to see small numbers, but like it's centered around 4. That's kind of what it's saying. You can expect to see that. There are also conditional expectations, and they're very similar. It's like what's the expected value of the random variable m given that we know that the blue spinner landed on a 1. All right, given that that happened. Like, what are the odds now? So it's like, all right, if the blue spinner landed on a 1, either you're here, here, or here, I guess, right? So it's just like you have 3 options total if you know that the blue spinner landed on a 1, and the random variable could be 2 again, could be 2, with probability 1/3, right? Because it's 1 out of 3 options. Now, if we know that the blue spinner was 1, we're conditioning on that. 2 times 1/3 plus could have been 3, because it could have been 1, 2. And the odds of that is, again, 1/3, right? 1 out of 3. Plus, could have also been 4, could have been 1, 3. And the odds of that for happening from your random variable is, again, 1 out of 3 chance. And so you can kind of see that it's kind of centered, again, around 3. And so you can expect, if you know, given that the blue is a 1, you can expect the random variable gives back 3 on average. Because like sometimes it's 2, sometimes it's 4, they cancel each other out almost. 3 is in the middle there. I hope that makes sense. That's kind of like what you can expect to see from your random variable, all right? And so here's a question for you now. Let's say that we are going to roll dice this time, but to make it more interesting, we're going to roll 2 dice, and we're going to make a random variable not to calculate the sum of the values on the dice, but this time it'll be the product. More interesting that way, all right? So let x be a random variable whose value is the product of the numbers that you see on the 2 dice that you're going to roll. So one potential outcome of like your experiment is like it lands, like the red die lands on a 2 and the blue die lands on a 3, yeah? And so let's define x to be the random variable that like it assigns one big number to that outcome, which is 6, the multiplication, the product of those 2 things, all right? And so there's a bunch of different ways to get 6, like it could have been 3, 2, it could have been 6, 1, it could have been 1, 6, right? But let's keep track of all of them, all right? That's what we're doing. That's what I want you to do right now. So please, given that, calculate first the range of this x random variable, like what are all the different values that it could take on, because it's not going to be just 1 through 36 anymore, or like 1 through 12 if it's the sum. It's not going to be 1 through 36. There's going to be some numbers skipped because of multiplication. So think about that. You can write a program. I think that will help you. And then also talk about the distribution of the random variable. So make one of these tables. What is the distribution of the random variable x? What are the probabilities of each of those numbers getting out of it? And then also, finally, what is the expectation? What's the expected value of that random variable x? What value you can expect to see, all right? So I think that's what I want to ask. Give that a try, write a program, and I'll show you my answer. All right, so for the range of x, I wrote a program to do that. I think that's the easiest way to do it. So here's my program. I'm just keeping track of, like, first of all, total outcomes, which I know is going to end up being 36, but just for fun, I'm going to do that anyway. And then here is, like, I'm ranging. Here I am rolling my 2 dice. Red die is die I, the blue die could be die j or something. And so the event itself is like the pair ij, so I can turn that into a list. And the outcome, the value of the random variable is that product, all right, I times j, all right? Those are the 2 values. And so, yeah, I'm just going to keep track of, like, how many times I saw this product or something. And so I'm using a hash table to keep track of counts. Like, all right, this product, put it in there 0 times if we haven't seen it before, but, like, add 1 to it if we have, stuff like that. That's what I'm doing, all right? So that's what's going on. And, yeah, I'm just, like, keeping count of stuff. And I can use that to calculate eventually the expected value, all right? So here I am looping through what I've seen. So here I am running it. Let's do that. So here is the output of this program. What it's doing is it's making it in the hash table. It's keeping track of how many times it saw that particular product. Like it's doing the calculation for the random variable, like what is it taken on, and from there it's going and like keeping track of things. So like it sees that the product of the 2 dice could be 1 only once, because like 1, 1 makes that one. And for 6, there's 4 options, right? There's the 2, 3, the 3, 2, the 1, 6, the 6, 1. So it kept track that there were 4 ways to do that, all right, to make a 6 come out of the random variable. So yeah, that's just me printing that in this code right here. Here I am just like printing. I'm looping through the hash table, calling the first thing outcome, the second thing count, and I'm printing those out. So here is that. That's going to be, here's the range, right? This is the range. These are all the different values that the random variable could take on. See that there's some numbers skipped, right? It's 1 through 36, but like some of these numbers are skipped because of multiplication. So that's how you can calculate the range. And then this would be the distribution right here. It's like there's one way to make 1 as your output random variable. There's one way to make 36. There are 4 ways to make 6, for example. All right, that's the distribution. And then finally, the expected value is going to be like, if you know that there's 36 total outcomes, right? Because there's 6 options for the first thing, 6 options for the second thing. Let me use a different color so I can highlight that better. 36 total outcomes, if you didn't calculate that already. And then the way to calculate the expectation is, I think this way is the easiest since we did them separately. We counted how many ways for like the random variable to appear that way. So we can easily go from that to probability. Like there's, you just take the value of your random variable, multiply that by the probability that it took on that value. 1 over 36. 1 times 1 over 36 plus like 2 times 2 over 36 all the way to like 4 times 3 over 36, right? Plus 6 times 4 over 36 is a 4 out of 36 chance that it took on the value 6. That's what you can do. And so that I'm also calculating that here. So like expected value is like, I'm just adding into a variable, summing into that, multiply the value that we got out, like the 6 times 4 over 36, the count of it over the total outcomes. So that's how you can calculate the expected value, and that is apparently 12.25. So you can expect, on average, to see your random variable that represents the product of the values on 2 dice as you're rolling them. They're fair dice. It's a little over 12. Interesting. I think that's pretty cool. All right, so yeah, programs really help us here. And yeah, let's keep on trucking. Here's another example. Or not really, it's a new idea. It's really, really powerful. If you have 2 random variables, it just so happens that if you want to calculate a new expected value based on old expected values, you can solve for it very easily. The expectation is a linear process. All right, so here's what that means. So let's say that we got 2 random variables, x and y, and let's say that they have to be on the same sample space, though. You can't combine them unless they're on the same thing. Like x calculates maybe the sum and y does the product or something, but like it's on the same sample space. If you have those, and you also have c like a scalar number, like you want just a real number, here's a very easy way to get at something that you might want. Like maybe you want to know the expected value of like the sum of your 2 random variables. Like if I add them together, what can I expect to see? And linearity tells us we can prove that that's equal to their individual expectations summed together. That's really, really powerful. It's like the expectation can distribute over that addition. That's really cool. That's what linearity means in like a math class. And then same for this other one. If I want to know the expected value of me scaling my random variable by a certain value, well, I can bring that thing out. That's what this says. I can prove that this is equal to just take the original expected value and just multiply it by that scalar thing. So that's really, really nice. Saves us a lot of time, and we can prove this. So we can prove it. I'll do the first one, and then the second one is the same style. So like the expected value of the sum of those 2 random variables, well, how do you compute expected value? It's like either this calculation or this calculation. I guess this one's easier this time. You just like sum over all the sample space, multiply the probability that you got that event times the value that your random variable gave you back, right? So if you want the summed random variable, you're just going to like, all right, for every sample space value, take the probability, and then like it's going to be what x gave you back on that thing plus what y gave you back on that thing. Does that make sense? It's like that's what that calculates to be, like if you just do it all out. And then we know that like multiplication, of course, distributes over addition. This is just normal numbers at this point. And then you can turn that into, like you can split that up into this, right? That becomes that. And so that's like the sum of all this stuff. All this together is like in parentheses. And then like you can just sum over both of these separately, can't you? It's like that's just this plus this, right? That's exactly the same as this. But what is this but just the expected value of x? What is this but just the expectation of y? Isn't that so cool? Like this is just that. And then this is just that. And so you can split it up, all right? So there's that one. And then, yeah, this one is exactly the same. I guess we have time to do it. Why not? It's just as easy. So like the expected value of you scaling your random variable by some constant is, well, you sum over, right, all of your sample space. So you take the probability and then you multiply the expected value on that event times your constant. Well, that's just a constant. If this is a summation, you can always bring a constant out of a summation. And so it's equal to c times that, but what is this, right? What is this but just the expected value of x? So if you already have those values, like, it's very easy to combine them. It's really, really cool. All right, it's very useful knowledge. And so here's a good example of that. So linearity of expectation. Let's kind of go back to almost the birthday paradox again. Let's talk about birthdays again. Let's pretend, at least, that the probability that somebody was born on a given day is random. And it's 1 over 365 rather than like 1 over 365.25 because we have leap years. So don't worry too much about that. But let's say that that's the probability for the sake of this example, that somebody's born on a given day. And let's say we got a group of 100 people. Let's calculate the expected number of pairs of people who have the same birthday. That is not a very easy thing to calculate. But with linearity of expectations, it becomes simple. All right. Without linearity of expectations, this would be a very hard problem. All right. So think about it. Like if you want to do probabilities, like what are the expected number of pairs of people in a group of 100? It's like you have to divide by how many pairs of people there are. So first of all, how many pairs of people are in this example? There are 100, choose 2, right? Pairs of people. We need that. Pairs of people. Oop. And so what is that equal to? That's 100 times 99 over 2, which is equal to, I did the math ahead of time, it's 4950. 4950. All right, so we're going to need that in a second. And then a very easy way to calculate, like, all right, how many people can you expect to have, how many pairs of people, excuse me, it's hard to explain. How many pairs of people can you expect to have the same birthday? All right. What we'll do is we'll make 4,950 separate random variables. And this is where linearity of expectations is going to shine. Let's make, this is the trick, you make P1, P2, these are all random variables, P3, P4950, 4,950 random variables, one for each possible pair, one for each pair of people in this group of 100. Let them all be random variables. Be random variables that are, and this is the value that they're going to take on. This is the beauty of this. They're going to be 0. Let the random variable be a 0 if that particular pair of people did not share a birthday, or 0 if the pair, it's just a number. You can take on any number. Let's have it take on this number. If the pair doesn't share a birthday, and let it have a 1. Let it be a 1 if they do share a birthday, and 1 if they do. Do you see how what we want now is this? We want the expected value of the sum of all of these random variables, P1 plus P2 plus P3, because the way that we define them gives us exactly what we want, right? 4950. Because if they're a 1 if they shared a birthday, a 0 if they didn't, and so this will give me the expected number, right, of people that shared a birthday, expected number of pairs of people who shared a birthday. And because of linearity of expectations, I can distribute that. I can just multiply the individual ones together, or not multiply, but like take the sum of all those individual expectations. This is equal to the expected value of just the first pair, plus the expected value of just the second pair. And then we're gonna do some nice tricks in just a second. It's like expected value of P2 all the way, plus the expected value of that last random variable that represented whether the 4,950th pair of people shared a birthday or not. If you think about it, these are all the same. The expected value of any one of those pairs of people sharing a birthday, expected value of any PI, that's equal to, well, it's a weighted average, right? What is the expected value? Just go back to this, right? expected value of a random variable, well, it's equal to the value of the random variable times, like the weighted average, the value of the random variable times the probability of that value being taken on, plus all the other ones. So weighted average over all of them. Well, probability of any given pair of people sharing a birthday, like it's either going to give back a 0 or a 1, right? A 0 if they share a birthday. 0 times the probability that that particular pair of people shared a birthday. What was it? What's the probability that two people, probability that they didn't share a birthday. So it's either a 0 or 1. I'm getting ahead of myself. So it's either a 0 or 1, and it's going to be a weighted average. So let's do that, plus 1. And you're going to multiply by these are the different values of the expected variable, these are the different values that the random variable could take on, all right, I got to slow down, times the probability that it took on those values. So it's a 0 if they didn't share a birthday, that pair of people. So what is the probability that a pair of people does not share a birthday? It's like the first person's born on any day, and then the second person was born on some day that wasn't that one. If you think about it, it's just 364 over 365. And then plus 1 times, right? It's a 1 if they shared a birthday. And what's the probability that they both shared the same birthday? Well, there's only one day that they could have shared, right? 1 over 365. And that's going to be your answer. That's the expected value of any pair of people, right? Given how we define things. That's just going to be, well, the 0 goes away to 0. That's equal to 1 over 365. Does that make sense? And so, now finally, your expected value, what's the expected number of pairs of people who have the same birthday? Because it takes on a 1 if they do, a 0 if they don't. That's what we were looking for, this value, which is now equal to 4950 times, because these are all the same, times 1 over 365. And so, you can expect, on average, in a group of 100 people, 4950 times 1 over 365, so just divided by 365. You can expect 13.56 people, 13.6-ish people to share a birthday. That's bigger than you might think, but on average, you can expect 13 people, maybe almost 14, to share a birthday in a group of 100. And that's kind of also going back to our birthday paradox. That's why it's so easy. It's so easy that at least 2 people share a birthday, because that's what the birthday paradox was saying. For 23 people, like, you can expect at least almost one person, right, to share a birthday. So you can think about it that way as well. But it's super easy to calculate based on random variables. We made a random variable in a nice way, like the 0 kind of made things cancel for us, plus a 1 if something was true, and then we noticed that linearity gave us the rest of the answer. It solved a lot of things for us. So that's very beautiful. It's wonderful. And now I think the last thing I want to talk about in these slides is one last kind of probability distribution. It's called the binomial distribution. We know that, we know about probability distributions in general, right? These are like distributions. They could be uniform. We know that word already. But here's a binomial distribution. All right, it's a cool one. It's where you have an experiment, and there's only 2 kinds of outcomes. It's like success or failure. We define one outcome as success and one outcome as failure. All right. So, for example, a good example for the binomial distribution is coin flipping. So, for example, let's say you want to flip a coin. You can define like your favorite side of the coin to be success, and the other side to be failure. All right. So the distribution over a random variable that you define as the number of successes, all right, so there's a lot involved now. The distribution over the random variable defined by the number of successes, so it's not even a probability distribution, it's a random variable distribution. That's what I should have said. This is the slide I should have gone to, sorry. We call it the binomial distribution, all right? So, very interesting, right? So here it is solved out. The probability of exactly k successes in a sequence of n independent Bernoulli trials, we say. So this is just like you flip the coin and your previous flip does not influence the next flip. They're all random, they're all independent. Where the probability of success is p and the probability of failure is 1 minus p. It can only be one or the other, right? Which you can also call q, is equal to this. N choose k times p to the k, q to the n minus k. Because it's got to sum up to n, right? And that's it. That's what you do. All right. So, for example, we can use this fact, the binomial distribution, these Bernoulli trials, to come up with a probability of flipping exactly 2 heads if we toss 4 coins. All right, so if you think about it, what are all the different ways that that could happen? Flipping exactly 2 heads after tossing 4 coins. Like either like the 2 heads come first, like head, head, tail, tail, or like the heads stay together, tail, head, tail, 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 head, or the heads are separate from one another, like they're either on like both sides. There's that one, or like it's head, tail, like these are all the options. You have to think about it, but like this gives you the answer immediately. Or it could have been what? Tail, head, tail, head. I think those are all the ways, right? Those are all the ways to get exactly 2 heads after you toss 4 coins. Like you can figure that out very easily with this formula now. All right, so it's going to be just like immediately. You can say, all right, the way, if I'm tossing 4 coins, I want 2 heads. Let's say that heads is success, tails is failure. Doesn't really matter because it's 2 of each. But it's going to be 4 choose 2, right? 4 choose 2. 4 choose 2 times the probability of success to the number of successes. So there's 2 successes, let's say. So it's 0.5 to the probability of, or to the power of the number of successes, or 2. And then times the other probability of failure, which is also 1.5, or sorry, 0.5 times 0.5 to the, like, you got to fill in up to 4, right? The probability that it succeeded twice and with 4 trials, so that means you also failed twice. That's that. That's equal to 4 choose 2. That's 4 times 3 over 2, right? Which is exactly 6. I did them right. That's how you can figure out how many options there are. And then, all right, times 0.5, like you got heads twice and tails twice. 0.5 is really just 0.5 to the 4th power. And apparently, I did the math ahead of time, that's equal to 0.375. So it's decent chance that you roll exactly, or not roll, but you flip exactly 2 heads. Okay? I think that's what I wanted to say for that one. And so yeah, you don't have to write them out. There is a formula for it, all right? But it's involving random variables and expected values secretly, if you think about it. That's pretty cool, all right? But now you definitely see where that choose something else comes from, right? Because you want 2 heads, but order doesn't matter, right? That's like you're picking them out. It's a combination. So, okay. We can also talk about the expected number of successes, all right? Expected number of successes, we can play this game all over again of like saying 0 or 1, which is very useful for us, and use linearity of expectation. So, okay, expected number of successes, if we make n trials, like we flip n coins or something, the expected number of successes for each trial, call it like x sub I, is going to be, so for each trial, the expected number of successes is going to be just the probability times a 1, right? 1 if it worked, 0 if it didn't. So it's like the probability of success times 1 plus probability of failure times 0. That's going to count, right, for you. That's the expected number of successes. It's like it's the probability that it took on that value plus the probability that it didn't. And the zeros will cancel. That's beautiful for us. And that just ends up being p. And so in total, it's like for every coin flip, the expected value of each coin flip, CI, is the probability of flipping your coin on whatever you wanted, 0.5. All right, so it's very easy now. If you have n trials total, the expected value, the expected number of successes is just n times the probability of success. Isn't that so cool? Because of linearity of expectations. Because we want really this, right? What's the expected value of some constant times x? That's equal to constant times the expected value of x, which is just equal to, in our case, constant times the probability of success. So like if we have 3 coins, the moral of the story is like, what's the expected number of heads that you'll see? If you have 3 coins, just immediately it's 3 times 0.5. You can expect to see 1.5 heads on average if you roll 3 coins. Does that make sense? That's the binomial distribution. That's what it's giving to you. All right. So that's pretty cool. And yeah, I think that's what I wanted to say about that. So that's very helpful, very useful stuff. So here's my question for you. Give this a try. All right, so let me read it to you and explain it. But it's a fun one. It's a good use case of this. So let's say we got a gambler, and the gambler making a bet with you, I guess. And the gambler has a coin And he's telling you that that coin that he's got in his hand is either fair, it's a good coin, where it's equal probability heads or tails, like you got your fair coin. He's saying like, all right, either in my hand I have a fair coin where it lands on, as the fair coin, it lands on heads or tails 0.5% of the time, it's fine, or 0.5 probability time, so 50% chance heads, 50% chance tails, or he's saying either I've got this coin in my hands or I have a loaded coin. I have a fake coin, a biased coin, where the probability of heads is equal to 0.3 only. So either I'm holding the fair coin or I'm holding this biased coin, where the probability of heads is only 0.3. All right, and you're not sure which one he's holding. It's like they look the same. So without knowing, if you didn't know, right, which coin he's using, you tell him, flip the coin 10 times, and I'll make a bet as to which coin I think you got in your hand, either the fair one or the biased one. So you tell him to flip the coin 10 times, and you record the number of heads you see. All right, and you're like, all right, you make a plan in your mind that if the number of heads is at least 4, you're going to decide that the coin must have been fair. All right. If the number of heads is less than 4, you're going to decide that the coin must have been the biased one. All right. You could be wrong, but that's your strategy. All right. So here are your questions now. What's the probability that you were wrong if the coin was really fair? All right. What's the probability that you reach an incorrect conclusion if the coin is fair? So what I mean by that is if it's fair, but you thought it was biased, that means you saw less, what is it? You thought it was biased because you saw less than 4 heads, but it really was a fair coin. And then also, what's the probability that you were wrong in the other way? Probability that you reach an incorrect conclusion if the coin is biased. So you thought that it was fair because you saw at least 4 heads, but really it was the biased coin that got you that. What's the probability that you were wrong? It's going to involve the binomial distribution. All right, so give that a try. This equation is going to come out very useful and very important. So give that a try and see if you can get it. All right, let me just do it down here. So the probability that you were wrong if the coin was fair means that you thought it was biased because you saw less than 4 heads. All right, so that means you saw less than or equal to 3 heads. And so if you think about it, what we want to find now is the probability of, what's the probability that we saw 0 heads with the fair coin plus the probability that we saw 1 head with the fair coin. You kind of see that? 1 head with the fair coin plus the probability that we saw 2 heads, because those are all the ways that you saw less than or equal to 3 heads with the fair coin. What's the probability of that happening? Only 2 heads when you're really going to roll it or flip it 10 times. Only 3 heads when you're going to flip the coin, a fair coin still, 10 times. Right? So those are 4 separate probabilities, and we can calculate that, right? So that's going to be equal to, like for this one, probability that you saw 0 heads. 0 heads, 0 successes is 10 choose 0, right? 10 choose 0, which is going to end up being 1, times 0.5, which is the probability of success to the 0th power, because we saw 0 successes, and it's a fair coin, so it's 0.5 for success and also 0.5 for failure. 0.5, we failed 10 times. That's that one, plus the probability of seeing 1 head, right? That's going to be, how many ways are there to see just 1 head? Anywhere in your flipping of 10 coins. 10 choose 1 times probability of success for the fair coin. You saw 1 success. Probability of failure for the fair coin to the number of failures times that you saw. And I did this ahead of time. The answer for that is, there is a probability. It's a non-zero probability, but it's pretty decently small. It's 1.172. So it's 17-ish% chance that you were wrong with this strategy and the coin was fair. Right? So you have a decent chance of betting and winning, right? Usually, if you're going to play this game a few times. And now, question B is the flip side, right? It's saying, all right, what's the probability that you were wrong and the coin was biased? So you thought that it was fair. You thought that the coin was fair because you saw at least 4 heads, but it was the biased coin. So we now need to calculate the probability that we saw greater than or equal to 4 heads with the biased coin. So what's the probability that we saw greater than or equal to 4 heads with the biased coin, which ends up being the same as the probability that we saw just 4 heads with the biased coin, right? Plus the probability that we saw just 5 heads with the biased coin. 5 heads. Does that make sense? Plus all the way to that we saw 10 heads with the biased coin. This is a great way to end these slides, by the way, because just the idea, just the whole mathematical field of probability came up because it was invented because people liked to gamble and they wanted to see they wanted to calculate their odds of winning. So all right, that's how you calculate it for the probability with the bias coin. That will give you the right answer. So all right, what's the probability that you saw exactly 4 heads with the bias coin? So it's 10 choose 4 successes times the probability of success, right? Which is 0.3 this time with the bias coin. Probability of success to the power of how many successes you saw. That's 4 times the probability of failure. That's 0.7, right? To the power of how many failures you saw. So if you got 4 heads, it's 6 failures, right? Because you flip the coin 10 times. So all that, all the way to the 10 heads, and I did that ahead of time as well. That is a 35% chance that happened. 35% chance that you were wrong and the coin was biased. All right? But you thought it was fair because you saw more than 4 heads. So it's still, like, the odds are in your favor still, but it's a little bit more likely that you were wrong and the coin was a biased coin. Isn't that interesting? So I think that's really cool to just be able to calculate that, and hopefully you kind of see where it's coming from. It's like these things could have appeared in any order, so that's where the combinations come into play. All right. So yeah, the last thing I want to show you is not really a question for you or anything. It's just a fun example that kind of ties this all back to computer science. So like, we care about probability. Like, why are we learning about it? We're not trying to gamble. We're trying to write good programs and analyze them better. So writing hash tables and hashing, making sure that they don't fill up, right, is a very good example. So like the goal, right, of you make a hash table and you have a hash function is like you want each bin in your hash table to be equally likely for every value, right? Because you don't want them all to like collide. Like you don't want to like focus your efforts. If you have a bad hash function, like you leave a lot of these things, a lot of the slots blank, but like they all are like forced to go here, and like you do like open hashing or something. Like you have a big long linked list of things because your hash function sucks and you take everybody there. You don't want that, right? So what you'd like is to calculate probabilities. Like, what's the probability that I collide in a hash table if like I have a perfect hash function? Like, how big should my hash table be to ensure that I don't have a collision so often? That's what you want, all right? That's what you want to calculate. So we can do that now with our knowledge. So like, what's the probability of a collision in a hash table when you've got n slots to fill and you've got m things that I want to insert, m values to insert, all right? So what's the probability that those keys don't collide, all right? Or what's the probability that somebody collides, all right? At least one collision happens. Well, we know that could be solved with the complement. It's probably going to be much easier to calculate what's the probability that there's no collisions in my hash table. I'll subtract that from 1, right? And then, all right, how do we calculate that? What's the probability that there are no collisions? Well, it's equal to, these are, I guess, independent events, right? What's the probability that the first key doesn't collide? 100%, right? 1/1. What's times the probability that the second key didn't collide with the first one, times the probability that the third key didn't collide with the previous 2. It's the birthday paradox kind of calculation all over again, all the way up to the probability that the nth key didn't collide with the n-1 that came before it. Do you see how that's what you'd calculate? And so yeah, in the best case, like all your keys are perfectly random, every slot was equally likely, you had a perfectly good hash function that was as good as it could be, taking you on average to anywhere you could want to go. So this would end up being this, like what's the probability that the first key didn't collide? 100%. You got plenty of room for that. Times the probability that the second key didn't collide, assuming your hash function was perfect, would have taken it anywhere. It's n-1 slots left that are not in use, right? Times the probability that the third key didn't collide. Well, it's the probability, like the way that like it needed to choose from one of the other ones, right? You've got 2 slots in use, pick one of the other ones. The probability that happened was n-2/n, all the way down to that. Does that make sense? So yeah. for example, like if n is 2 to the 32, like you're gonna you have that many slots to fill, 2 to the 32, you got 32 hash values, and you want to insert this many things, 77,000 things. Even though you have like 4 billion places, you have 4 billion slots. That's what 2 to the 32 is, right? It's 4 billion-ish. 4 billion, 4.2, almost 4.3 billion slots to fill. Even if you put under 100,000 things, the odds of you colliding are 1 in 2 chance, 50-50. Isn't that crazy? So yeah, it's the birthday paradox, honestly. It's like it's very common, like you're going to share a value even if you have a lot of wide space to fill. It's very common to collide, all right? So if you do well, right, you have even more slots, add even more slots, then like you can add more things until it becomes very possible to collide. So yeah, usually you want to have as many slots as possible, and you want to be inserting as few things as possible in those slots. And so it's just a fun graphic to look at, like to see like where things are. Like here's the odds of dying in a shark attack, like at 1 in 100 million. The odds of you colliding if with 4 billion hash slots, 4 billion slots in your hash table, and you're inserting 10 keys, is on the average the same as you dying in a shark attack. Isn't that interesting? I think that's fun to think about. So yeah, this is just a fun little slide to show at the end of all this, because we can calculate this stuff now. All right, so that's tying things back to what we know, and I think that's what I wanted to say. That's where I want to end things. So you are now experts at probability. You can go to Vegas and win lots of money. All right, or also analyze your hash tables very well. So I think that's where I want to leave us, and I will see you in the next video.